Hi, my name is Ashley Molnar, and today I will be talking about using MLR statistical methods to predict future medical expenses. In this presentation, I will introduce the process of determining health insurance premiums and provide characteristics on the dataset. I will then go through my steps for preliminary analysis, model building, diagnosis, and validation, and I will end the presentation with a final model report and applications. To provide background on health insurance, it is a contract that requires a health insurer to cover some or all healthcare costs for a policyholder in exchange for paying a premium. There are private insurers such as Blue Cross Blue Shield and government insurers such as Medicare or Medicaid. Some factors that are used in determining premiums include type of coverage, amount of coverage, personal information, and competition in insurance industry. The cost of a premium is calculated by an actuary who assesses the likelihood of risk or perils and the costs associated with these risks. The insurer then relies on premiums to afford the costs of the policyholders. Being able to accurately predict future medical concerns and related costs would aid insurers in determining the best premiums for their policyholders. In regard to what has already been done to predict future medical costs, current research suggests there is a correlation between gender, age, height, weight, body fat, health checks, and diagnosis in determining future medical costs. However, it was also found that the best indicator for future costs is examining previous medical expenses. Some models attempt to predict premium costs for insurance by evaluating current enrollment and insurance market regulations, while others focus more on age, gender, and socioeconomic status. Medical insurance charges data was found using Kaggle.com at the link provided. The data has a sample size of 1,338, and the explanatory variables were collected on insurance policyholders to determine their age, sex, BMI, number of children, whether or not they smoke, and the region they live in the United States. The response variable is their yearly medical expenses billed by the insurance holder. During the screening process, it was found that the data was clean with no missing values. The explanatory variables being investigated in this project are age, sex, BMI, children, and smoker. With my background in biomedical engineering, these variables seemed most interesting to investigate. For the rest of the project, sex will be referred to as female because the variable was set to 1 for female and 0 for male, and smoker was also set to 1 for those who smoke and 0 for non-smokers. The two primary research questions being investigated include: are the variables age, sex, BMI, children, and smoker all significant predictors for medical insurance charges? This can be investigated using a global test. And the second question is, which variable has the greatest partial correlation with insurance charges, which can be calculated using a type 2 ANOVA test. In order to perform a preliminary analysis on the data, the correlations were taken between each pair of explanatory variables. From this, there does not appear to be a multicollinearity problem, and this was supported by the scatter plot to the right. Next, a residual plot was done, which showed that there may be issues with non-constant errors, the data violating a normal distribution, and influential points. Next, the correlation was taken between the explanatory variables and the response variable. From this, it was shown that female does not have a high correlation with charges, while smoker appears to have a high correlation. The first model developed is shown below as a first-order model. This has a multiple R-squared of 0.7497 and an adjusted R-squared of 0.7488. Diagnostics were then performed on the first-order model, including the Shapiro-Wilk test, Brown-Forsyth test, and influential point or outlier test. The Shapiro-Wilk test provided a p-value of 2.2 times 10 to the negative 16, meaning we would reject the null hypothesis and that the data violates from normal distribution. This was further shown by the QQ plot on the right. The Brown-Forsyth test determined that the difference is statistically significant, meaning we would once again reject the null hypothesis and that the residuals have non-constant variances. When investigating the influential points, it was determined that 3 points would be influential based on the hat value. These points are 544, 1048, and 1086. Based on the model failing the Brown-Forsyth test, the Shapiro-Wilk test, and having some influential points, it was determined that the model should undergo Box-Cox transformation and WLS and robust regression remedies. It is important to note there is not a concern about linearity or multicollinearity in this model. In order to transform the data, the Box-Cox transformation was used, and the lambda was found to be 0.1515152. The transformed model is shown below with the summary at the bottom right. This shows an improved R-squared of 0.7731. After performing the Box-Cox transformation, the diagnostics process was repeated to determine if it resolved any of the model's issues. First, the Shapiro-Wilk normality test provided a p-value of 2.2 times 10 to the negative 16. This means the data violates from normal distribution, which is also shown in the QQ plot. The Brown-Forsyth test determined that the difference is statistically significant, meaning the residuals have non-constant variances. Additionally, the influential points were determined to be 1048 and 1086. Moving forward, WLS and robust regression will be used to hopefully resolve these problems. Best subset analysis was then used to determine if any variables could be dropped from the model. As shown in the boxes on the right, it was between two models. One with a p of 5 in which female would be dropped, and one with a p of 6 in which all of the explanatory variables would be included in the model. When comparing the two, it varied based on which area one improved and one declined. For example, when examining dropping female, the SSE value increased to 94.09159, while the AIC value decreased to negative 354.1.939. From this, it was determined that k-fold validation would be used to determine which model would be best. When comparing the two, the R-squared values were similar, which led to the decision that the best model should be chosen based on the lowest RMSE value. That would be the model that would drop female with a value of 6067.901. Therefore, female would be dropped from the final model. Next, the remedies were performed on the model, including WLS and robust regression. WLS greatly improved the model after 3 iterations, with a new R-squared value of 0.9318. However, when robust regression was performed, it made the beta for BMI become negative. This was concerning because BMI showed a positive correlation with the insurance charges, and I was concerned about the accuracy of the model. Therefore, I decided to not include robust regression and to only include WLS in the remedy. After performing remedies, the diagnostics process was repeated to determine if the model was improved. The Shapiro-Wilk normality test provided a p-value of 2.2 times 10 to the negative 16. This means the null hypothesis would be rejected and the data violates from normal distribution. The Brown-Forsyth test once again showed that the difference is statistically significant, meaning the residuals still had non-constant variances. Additionally, the influential points were determined to be 604 and 718. From this, it was determined that advanced measures would be necessary to improve the model. Also, it is important to note that the outliers were kept in the data. This was done because the outliers were high dollar values, and since this model would be used to predict premiums for insurance companies, it would be more important to overestimate the premium than to underestimate. This is because when a policyholder has a very high medical charge, it would end up costing the insurance company and they would lose money if the premium was not high enough. Therefore, these outliers were left in the data. In order to investigate the first research question, a global test was performed. From this, the F statistic was shown to be 4,554, and the critical value was found to be 0.1775949. Since the test statistic is greater than the critical value, we would reject the null hypothesis. This means that the variables age, BMI, children, and smoker are significant in predicting future medical costs at the 95% confidence level. Then, a type 2 ANOVA test was performed to calculate the partial correlations for each explanatory variable. For age, the partial correlation was found to be 0.2508. For BMI, it was found to be 0.0132. For number of children, it was found to be 0.0225. And for smokers, it was found to be 0.2439. From this, it was gathered that age and smoking have the greatest partial correlations. This was to be expected as older age and smokers tend to have higher medical costs. When comparing the original model to the current model, it is apparent that there was great improvement. The original R-squared value was 0.7497, while the new R-squared value is 0.9318. Meaning the new model explains 93.18% of the data. The new model is shown below in order to predict future medical costs. However, it is important to note that moving forward, more advanced remedial measures would be necessary to address the failed Shapiro and Brown-Forsyth tests.